This is the 12th lecture in the FOA series about fiber optics. The next few lectures are all going to be about fiber optic testing. To begin with, what needs testing? Well, fiber optic components are tested at the manufacturer. Components are tested at incoming inspection by the people who purchase them. And they're tested while they're in the process of being installed in cable plants. And finally, complete networks are tested after they're all put together to ensure that they're working properly, or if not, to troubleshoot them. Manufacturers test components as they're developing them, in the research phase and development as they're getting ready for manufacture. During the manufacturing process, they'll test what needs to be tested to ensure the product meets its specifications. And then, after manufacture, a certain number of products will be retested for quality control. When components are tested at an installation, they'll generally be first tested upon receipt, generally at the job site, to make sure that the proper components have been received. They'll be tested again during installation. For example, when splices are made or connectors are put in. There'll be final acceptance testing after the complete cable plan is finished to make sure that it meets its loss budget. If there's a problem, there'll be testing for troubleshooting and finding it during the installation. And of course, later on, there'll be testing for restoration in case something happens, like a cable cut, that requires the cable plant be repaired. What gets tested depends on who you are and what you're interested in learning. Fiber manufacturers test fiber for geometry to make sure its dimensions are correct, the attenuation coefficient of the fiber, and the bandwidth. Cablers test the attenuation coefficient and often the bandwidth. But when you're installing a cable, you're primarily going to be interested in the end-to-end loss of the completed cable plant. So unless you're using an OTDR to ensure that you don't induce any bin-related losses due to stress in the cable, then mostly what you're going to do is test the end-to-end loss when you're finished. For connectors and splices, we're interested in the loss, the light lost at the connector. And mostly for connectors, we're interested in reflectance, the amount of light that gets reflected back toward the source, because that can be a problem in high bitrate systems. Connectors and splices are qualified at the manufacturer. They will terminate many cables with their connectors to see what the average loss is when terminated in typical fashion. But the end user who's going to be putting these connectors on their cable plant will be testing in the field to confirm proper installation. The installer is going to look at the end-to-end cable plant loss, which will include all of the fiber, all of the connectors, all of the splices, all of the patch cords, everything that builds up the end-to-end cable plant that they'll be running their communication system on. For long-haul networks, they'll typically shoot OTDR traces so that there'll be a record of what the cable plant looks like, so if in the future they need to do restoration or troubleshooting, they have a record. Very long systems will test chromatic dispersion, polarization mode dispersion, and typically spectral attenuation because they'll be running wavelength division multiplexing. The actual tests involved will depend on the fiber type, the installation type, the network type, and more. The simplest form of testing is continuity testing, which confirms that the fibers are continuous and they're connected properly. Since fiber networks use two fibers, one transmitting in each direction, polarity is important to ensure that transmitters are connected to receivers and vice versa. Typically, continuity testing is done with a visual tracer, which might be made out of a flashlight or a simple LED, or a visual fault locator, which uses a red visible laser source. Visual fault locators, the high-powered lasers, can do more than just trace fibers. They can actually look at fibers, find areas of high loss that can be caused by installation problems, or they can find breaks in fibers, particularly good in things like splice trays, where damage to the fibers almost always is impossible to find when it's so close to the splice. But you have to remember that visual fault locators only work on buffered fibers or translucent cable jackets, typically from single-mode fibers. Connectors are visually inspected with a microscope. The microscope is used when you do the actual termination to check the quality of the polish and find scratches and cracks in the fiber. But fiber optic microscopes are used all the time as a tool to find dirt or other contamination on connectors. They typically have a fairly high magnification, 100 to 400x, and two types of illumination. Direct down on the fiber so you can see the core if you illuminate it, and from the side because that shows most of the detail on the surface finish. A standard test with fiber optic instrumentation is optical power. For example, how much power comes out of a transmitter or is received at the receiving end of a communication system. Power meters are also used for loss testing, as you'll see in a minute. It's basically a specialized light meter adapted to fiber optic connectors and calibrated at the proper wavelengths, usually 850, 1300, and 1550 nanometers, and the calibration is traceable to international standards. Insertion loss testing uses the power meter and a matching light source to simulate actual system operation and measure the dB loss of the link. The light source should be similar to the source used in the transmission system, either an LED or a laser, and you use reference cables to mate up to the cable plant you're testing in order to be able to condition the light going into the system and test the connectors on each end of the cable plant. Optical time domain reflectometers use an indirect method of testing the fiber optic cable plant. They use the backscattered light, which is the main cause of loss in an optical fiber, to create a trace or a picture, a snapshot if you will, of what goes on in the fiber. Using that snapshot of the fiber, you can measure connector loss, splice loss, and the attenuation coefficient of the fiber. You can also measure the length of the fiber, and you can find faults in the fiber. OTDRs are very, very useful instruments, but they're also complex, and they need a lot of training in order to understand how to interpret an OTDR trace. Very long distance networks need special testing, primarily for the dispersion that limits the bandwidth over long distances, chromatic dispersion and polarization mode dispersion, and then they need to be tested for spectral attenuation because dense wavelength division multiplexing uses a wide spectral band in the fiber, and the fiber must support all of those different wavelengths for the entire length of the span. This is just intended as an introduction to fiber optic testing. There's a whole series of testing lectures following this that will give you more details on things like insertion loss testing, OTDR testing, the differences between them, and all the specialized testing that are required for various components and systems. So see the other YouTube videos as they are added to this lecture series. We're the FOA, the Professional Society of Fiber Optics. We hope you enjoy these lecture series, and you can find lots more on the technical details on fiber optics at the FOA website, and especially the FOA Reference Guide to Fiber Optics, where there are hundreds of pages of technical information.